Hi everyone, it's Mads again and welcome to this episode of our lesson. This episode will be focusing more on motion graphs. This means that we're going to interpret graphs as well as we're going to express data in terms of graphs. What I'm lecturing to you now is general knowledge. That means this will help you a lot when it comes to taking your entrance exam and taking your scholarship exam, because this is mostly commonly included in your entrance exam or in our standardized tests, like for example your scholarship exam and board exam. Okay, let's go to our objectives. So the objectives of this lesson are, at the end of this lesson, you are expected to determine the slope in the area under velocity time and acceleration time graph as well as position time graph. Second one is you are going to interpret the meaning of the slope. Take note of the word interpret. I am expecting that at the end of this lesson you can interpret data, or you can interpret graph, the slope of the graph related to motion. And you are also expected to interpret areas under the velocity time graph and the acceleration time graph as well as the position time graph. Okay, let's move on. Going back to this title, motion graphs. When we say motion graph class, this is very important topic in physics because we are going to look at the pictorial representation of data in an organized manner. When we say organized manner, we're not really using computations here, but we are going to present data in a pictorial way or by means of graph. So what is position time graphs? Position time graphs is a something like this one. You can read the definition, but I will just explain it briefly. We're using Cartesian plane and we'll be presenting data like this one. So this is in our mathematics, this is or y-axis and this is x-axis. But in this case, we're going to express this one as, since we know that position is equals to, or position represents as x. So this will be our x. That x is or representation of position. It's expressed in meter or length. Shall we say length? And this is this x here will be substituted by t, or which is time. The unit here is s or second. And basically, the position time graph is used to show an object position. Let me write here. Used to show an object position at a given time. Another one is I have said a while ago, if we want to graph or if we want to plot our position here is will be plotted at or will be placed at y-axis. So whatever the orientation of the position versus time graph, or whatever problems that we'll be encountering as we move along in our college life, you always put position at y-axis and the time is in x-axis or axis. And also when it comes to velocity time graph, obviously for velocity you will put velocity at y-axis and also time is still in x-axis. And if we have this kind of relationship, which is for example this one, x versus t, and our main target here is to, of course, get the slope of that line. And slope, we all know that slope, we have learned that in our mathematics, that slope is the ratio of a rise to the run of our graph. That means if this is x and this is t, this can be translated into something like this one. This is delta x, and this is delta, sorry, this is delta. Let's try to grab our eraser here. This is delta t. So this is delta t, in which we all know that rise over run here is just b equals to the rise here is equals to y sub 2 minus y sub 1 over the run here is x sub 2 minus x sub 1. This is also given by, since we all know that displacement here, change in displacement is equals to x sub 2 minus x sub 1 and t sub 2 minus t sub 1. So this is how we interpret, and this is how we describe or illustrate our graph in terms of position versus time. So let's move on to this one. Let's try to I will not give you a sample problem. Will not doing any computations here, but I will just present to you some of the common graphs that we'll be encountering, and we're going to interpret this one and get information from it so that you could easily understand what is really mean by this when you see this graph. So for example, we have this graph. Let us say this one is figure 1 and this one is figure 2. Maybe I could write here figure A, and this one is figure B. So for example, we have this graph. In terms of position versus time graph, I can also write x of t, or x versus t. When it comes to time versus or position versus time graph, if we have to compare this two figure here, the only difference is that the object here is not moving and the object here is moving. That means when you see the graph that has a flat line or horizontal line, represents the displacement, or the object is not moving because displacement is here. Basically this line must be located here, but for the sake of our naked eye, because we cannot see that easily, so let us put this flat line here. But I will show this one. I will demonstrate this one using PET simulator so that you can see it. Now in flat line of x versus t, this represents that object. I will put here some or details, information that can be derived from this graph. So when you see the graph that has a flat line, this means that object is not moving. Okay, meaning to say, if object is not moving, velocity here is 0. So that's how we interpret when you see this graph. In terms of, take note, in terms of position versus time graph. Okay, how about this one, figure B? When you see this graph in terms of still x versus t, so this is steeper line. When we say steeper line, before I forget, the slope here is, when you look at this slope, the slope of this line here is basically 0. Why 0? Because m here is 0, since this is the position, or the position of the object is not moving, only the time. That means that we cannot divide 0 or number over 0 because that's undefined. That means we can simply assume that the slope here is 0, and also the velocity is 0. If the velocity is 0, the slope is still 0. And for figure B, the slope is obviously not equal to 0. Meaning to say, our velocity here is not equals to 0. Instead, velocity here is positive. Why positive? Because the line here is increasing but in uniform velocity. Meaning to say, the velocity is not changing. Meaning to say, if we have a object here, for example, I will label, we have here starts from 0, 10, 20, 30, 40. Object is moving at a constant rate of velocity. So that is what this graph tells us. So the velocity is constant and velocity is positive. And when you see this graph, this kind of graph represents that velocity is constant. Let's move on to this one. So when you see this graph, assuming that we have here a two-line graph here, still this is a position versus time graph. That means the object is moving. So if we compare these two lines here, obviously the object here is obviously moving. Okay? The object is moving. But when you look at the orientation of the line graph here, the blue color here is steeper than the red one. That means when you see this graph, steepness of the line is associated with the rate of the speed, or shall we say velocity of the moving object. Meaning to say, if we have this blue line here, the object at this moment is moving very fast. So whenever the line is very steep, or the steeper the line, we'll just quote this one as the steeper the line, the faster the moving object is in terms of still x versus t graph. So meaning to say, if we want to get the information and compare the line here, the red line and blue line, we can simply assume that the object 1 reaches the destination very fast than the object 2, because it really consumes a lot of time comparing to the object here. That means they are moving at constant velocity. It's because the line here is still straight, as you can observe on our diagram. When you have this line of graph, also in this case here, acceleration here is, I will just add here, acceleration is 0 because velocity is not changing. And same with this one, if velocity is not changing, the acceleration is 0. Meaning to say, I can add here that acceleration is equals to 0. Okay, next graph. When you have this kind of graph in terms of position versus time graph again, so we have a curved line. So whenever you see this curved line in x versus t graph, represented as this one or with corresponding value, you will simply assume that the object is velocity of the object is changing. So meaning to say, if the velocity of object is changing, our acceleration is not equal to 0. Instead, acceleration here is positive, as well as the velocity is also positive. It's because it's increasing velocity. This is how we interpret the graph if the graph is looks like this one. Okay, let's try to compare this graph. It seems like they are the same, but yes, they're the same. but the only difference is that this one is steeper than that. So if we have this kind of graph, let's say this is figure A and this is figure B. If we have to compare this one in terms of velocity, they are both decelerating. Okay, take note of that. When you see this graph, this is the graph of deceleration. So they are both decelerating, but the only difference is that figure B is decelerating faster than figure A, because figure B is steeper than figure A in terms of the line here. Meaning to say, when you see this one, the slope here is negative. Slope is negative. Meaning to say, the velocity here, when you see this graph, the velocity here is negative, because slope is equals to velocity in terms of position versus time graph. This is the graph of a decelerating object with respect to position, or with respect to the time of the interval. Let's try to consider this one, a real-time example of the graph here that we have. So for example, we have a two moving objects here. Let us make a legend here so that we can understand it clearly. So let us say object 1 is the red car, and object 2 is blue car, obviously moving in a different speed or velocity. And in this part of the diagram here, we can see the actual graph of what is happening. So as you can see, let us go to object number 2. The object number 2 is the blue car that also corresponds to the blue line here. So let us label here the blue line. So blue line. And for red car, obviously that's red line. So in terms of the steepness of the line, as you can see, the red one is steeper than blue one, because in this part of the diagram here, we can see that the object number 1 is moving faster than the object number 2, as we can see here. That means the line, or the line graph that can be associated with the moving object number 1 is steeper than the line graph of the object number 2. Meaning to say, we can simply conclude that we can write here, the conclusion here is the steeper the line of the graph, the faster the object is moving in terms of x versus t graph. So that is the conclusion that can be taken from this diagram here. So we've done discussing about position. Maybe that's the last graph for position versus time graph. Now allow me to show you what is really happening in real life situation when we have this kind of graph here. So let us switch to our pet simulator, and let's try to do some experimentation regarding the movement of the object that has a graph like this one. So for example, I have here a position. Let's say the position of the object or the man is 0, and I will not put value here. since the velocity is not moving. And let's try to play this button and try to look at the behavior of this object and also the graph of that particular situation when we tap this button here. So I will tap it. So try to observe, velocity is not moving. So the velocity is still in the zero line here or zero value here, and also the position is also flat. So that is exactly what is happening in this diagram here. When the object is not moving, this is exactly what we have seen here. The graph of the velocity is 0, and the graph of the velocity position over time is still flat line. Although we have consumed 4.7 seconds, but still the graph is flat, as we can see here. The displacement versus time graph is having a flat line, which is the slope is 0, and when the slope is 0, the velocity is 0. Okay, another one is this one, this graph here. So let's try to demonstrate. Let's have a simple experimentation regarding this one. So the object here, as the velocity of the moving object here is not equal to 0, and probably I forgot to write, probably the velocity here is constant. Velocity is constant. I will just write big letter C for constant. So let's try to demonstrate that in this part of the diagram. Let's hit the reset all. Okay, for example, we put value here. Let's say 5 meters per second, and try to observe the behavior of the line graph here and also the behavior of the line graph here. So look at the graph here. Okay, the graph of the position versus time is something like this one. That means this is exactly the same with this, with the graph here, this one. So this is the demonstration that can be taken from, or this is the graph that can be taken from this situation. Okay, so let's move on to the velocity time graphs. So a velocity versus time graphs is a useful tool that can be used to describe motion with either constant or changing velocity. Any point on Sachs graph will have a coordinates that has this one. So time versus or velocity time graph. Now take note that B here is corresponding to our y-axis, and T here corresponds to our x-axis. So the slope of a velocity time graph represents acceleration. That means a slope, which is delta y over delta x, is equals to the acceleration of that moving object. We have already presented that in our video, in our motion along a straight line, that the acceleration is, or total acceleration or average acceleration, is equals to delta v divided by delta t, and this is equals to final velocity minus initial velocity divided by final time minus initial time, or just A is delta b of delta t. So let's try to study this graph. Still, this is V versus T. So we can put a unit here, meter per second, and here is second. So what is the difference between this graph? When you see this graph, let us say we have here a steeper line and this one is a flat line. In terms of velocity time graph, for this graph, the object is moving. Okay, do not be confused, since we are in V versus T or velocity time graph. When you see this line here, the object is moving but the velocity is constant. So to illustrate that, to show you that this is true, look at this one. Let's try to reset this one, and I will set a value here that's equals to maybe equals to 5 meters, and try to observe the line graph here that can be taken from this value. So as you can see, although we have value of 5 meters per second, but we do not change the value, in which still 5 meters per second. But if you change that into a certain value, like for example 0, the graph will also be changing. Okay, I will let's try to repeat the process. I will put, let's try to put the distance of -10 so that we have longer time. So we have 5 meters, yes, 6 meters. Let's try 6 meters per second, and let's try to play this one. So as you can see, the velocity time graph is flat line, but the object is moving. Now the object is at 4 meters from the original position. So the object is still moving, but the velocity is constant, not changing, which is 6 meters per second. So that is the justification of this line. Meaning to say, I can write here, in this line here, I can write, when you see this line, velocity is constant, and obviously object is moving, provided that this is velocity versus time graph. And when the velocity is constant or not changing, the acceleration here is 0. So the only difference between this graph is velocity here is not changing, however velocity here is increasing. So let's try to check this graph in our pet simulator. What is really happening when we have this kind of graph here? So I will try to reset my pet simulator, assuming that I will put 5 meters per second squared of acceleration here, and let's try to start from -10 so that we have longer time. Okay, now I will not put velocity here. I will not put a value of velocity, but instead I will put a value of acceleration, which is 5 meters per second squared, and try to observe the graph for acceleration and graph for velocity and also for time. So as you can see, the graph here is exactly similar to this graph here. So in terms of velocity versus time, this is the graph of the velocity, and as you can see, the velocity is increasing. Okay, try to observe again. 6 meters per second squared this time, and try to observe the value of velocity here. So as you can see, the velocity is increasing rapidly. So the velocity is increasing. That means this is exactly what is happening here. Velocity here, we can put that velocity, if you see this graph in your exams or in your scholarship exams, velocity is increasing, but acceleration, in terms of acceleration, as you can see here, this acceleration here is flat line, meaning to say the acceleration is constant. So we can assume that acceleration here is not equal to 0. That means the slope of this line, so this is also positive. The slope of this line is positive since our velocity here is increasing. So that's what do we mean by this graph. So when you see this graph, this is exactly what is the information that can be taken from that. So let's try this one. How about if we have this kind of graph? This is still velocity meter per second versus velocity versus time graph again. This is velocity in terms of second, velocity time graph again. So when you see this graph, this means that we have a slope of negative. So when the slope is negative, the slope is negative, there will be a deceleration. So this means that if the slope is negative, this is exactly what is happening to the so-called negative velocity. So when the object is moving and suddenly slows down at a point, so this is what exactly the graph is looks like. So object is started from a certain velocity, and at certain point of time it slows down until it stops. The graph is, to illustrate that movement or illustrate that situation, the graph is like this one. The slope is negative, so there will be deceleration. So basically, but still in terms of since this is just exactly the same with this one, but the only thing is this is oriented like this, but still we say here that we conclude that the acceleration is still not equal to 0, but in this case the acceleration is positive. In terms of this one, acceleration is not equal to 0, but this is negative, but still this is still a uniform acceleration. That means the acceleration is constant. When we say uniform acceleration, this is pertaining to constant. Okay? So this is constant acceleration but in a negative value. How about this one? So still this is again graph of velocity versus time graph again. So we have a steeper line. That means the object is moving, but the velocity, we can conclude that velocity here is increasing. Velocity is increasing, but the yellow line here, let's use yellow. The yellow line here, took longer time because, as you can see here, in terms of the time, the velocity is slower than the velocity of the green line. That is why, although the commonalities is velocity is increasing, but in terms of time interval, the yellow line here took longer time before reaching at a maximum speed. For example, they are in this line here. In this line here is the maximum speed, or shall we say top speed, meaning to say green line here is a higher value of acceleration than the yellow line here. Okay, so I think these are the common graphs that can be encountered in dealing with motion graphs. And I have already presented the basics or the information that can be taken from this graph. And now it's time for us to understand what is the area under this particular graph here. So let's move on to the next slide. So for example, assuming that we have this kind of graph here, let us say this one is velocity with respect to time, or I can just simply write here. I can just simply write as meter per second, and this is also with respect to time, and this is our line of graph. Now if we have this kind of graph here, which is velocity time graph, and for example we have here a line here. Shall we use, I think, shall we use white one, and we have this line here under this graph here, and we're going to have the slope. Basically the slope of this one is the acceleration, but how about the area under this shape here, or under this slope here? What is really happening under this area here, or what information that can be taken from the area under this geometrical shape here? Now basically this is the displacement covered by a moving object with respect to time when it comes to the velocity time graph. So we can say that the information that can be taken from the displacement here, or the shaded area here, part of the line here, is the displacement of our moving object. And if we have to translate this one, or if we have to magnify this shape here, we can say that so this is trapezoid. So if I draw a line here, this is a right triangle, and right triangle is given by a certain formula. Certain formula in getting the area of the triangle. But since this is one shape here, this is we can say that this is the height, and this one here is also another height of that shape. I can put height 1 or height sub 1 and height sub 2 here, and this is also the base of that shape here. So meaning to say, the area under this is equals to 1/2, since we have here a right triangle, 1/2 b times height 1 plus height 2. Now the area here is the displacement covered by the object. We can use this shape here, or geometrical shape here, in deriving some formulas relating to uniformly accelerated motion, where in fact by using this shape here we can, I think, derive at least 4 to 6 equations of uniformly accelerated motion, but we will not do that derivation here. But I just want you to know that by considering this shape here in terms of velocity time graph, we can derive at least 4 to 6 equations relating to uniformly accelerated motion, since this is the acceleration here is uniform but the velocity is increasing. Okay, that's example number 1. Let's put here number 1. How about we have here a graph of still velocity versus time graph again, because class, velocity time graphs is widely used in deriving equations for uniformly accelerated motion. That is why we're using this example here. So for example, we have here a graph that looks like this one, and obviously we all know this kind of graph in our previous slides, that the acceleration here, or yes, the acceleration here is negative. So we have a decelerating object. Now, the area under this graph of velocity time graph can be also represented by, again, displacement. So the slope is for acceleration, but the area under this line, or yes, is for displacement. And as we all know, this is something like right triangle. This is A, this is B, and this is C. Or this is, shall we say, this is the base, this is the height, and this is the hypotenuse of the triangle. Okay, now in getting the area under this triangle, we know this already, this equation in our geometry, in our basic mathematics, that area under right triangle is equals to 1/2 times base times height. So if we have to apply this equation, we will get displacement of that moving object. What if we have this kind of graph in terms of velocity time graph? What if we have this kind of graph here? And take note that this is, as we learned in our previous slides, this is constant velocity. That means when we have a constant velocity, acceleration is 0. So what is the area that can be taken from this under this area of a velocity time graph if we have this kind of graph? Obviously the slope here is acceleration, which is 0, but the area here is also pertaining or associated with the displacement covered by that object. And this is rectangle, and so if we have a rectangle, this is in our geometry, this is our base and this is our height. Since this is identical, the base is identical and height is also identical, the area here is equals to simply base times height. And by applying this formula, we can get the displacement of that object. I think I should stop here because I believe I have consumed a lot of time in explaining this one, but rest assured that I have already given to you the most important concepts and knowledge that you can be used not only in this lesson but in your upcoming entrance exams and scholarship exams. So I think we should end this lesson, and that would be all. If you have some clarifications regarding this lesson or the concepts that I have presented here, you are free to ask question in our group chat, and I will be happy to answer that queries. That would be all. Thank you so much for spending your time in this video lesson. See you in the next episode.